Welcome! In this session, we'll explore problem number 1546, maximum number of non-overlapping subarrays with sum equals target. We'll break the problem down, discuss possible approaches, and understand how to solve it efficiently. Let's get started. In this problem, you are given an array of integers, nums, and an integer target. The goal is to identify the maximum number of non-overlapping subarrays within nums where the sum of the elements in each subarray equals the given target. A subarray is defined as a contiguous section of the array, and two subarrays are considered non-overlapping if they do not share any elements. For example, if one subarray ends at index 2, another subarray cannot start at index 2 or earlier. You are required to return an integer that represents the maximum number of such valid subarrays. Additionally, keep in mind the constraints for the inputs. The length of the nums array can be up to 100,000, and the values within nums as well as the target can include both positive and negative integers, within the specified ranges. Let's start with an example to better understand the problem. If nums is 1, 1, 1, 1, 1, and the target is 2, the output is 2. Here's why: the subarrays, nums 0, nums 1, and nums 2, nums 3, each sum to 2. These subarrays are non-overlapping because they do not share any indices, and no additional subarrays can be formed that meet the criteria. Therefore, the maximum number of non-overlapping subarrays in this case is 2. This example demonstrates how we need to identify contiguous sections of the array that satisfy the sum condition while ensuring they do not overlap. Now consider another example. If nums is -1, 3, 5, 1, 4, 2, -9, and the target is 6, the output is again 2. Here, the subarrays, nums 1, nums 2, and nums 3, nums 4, each sum to 6. These subarrays are non-overlapping because the indices of the first subarray end before the indices of the second subarray begin. No other subarrays can be selected without violating the non-overlapping condition. This example highlights how the solution must handle both positive and negative integers in the array while identifying valid subarrays. In a third example, let's take nums equals -2, 2, -5, 5, and target equals 0. The output here is 1. The subarray, nums 0, nums 1, sums to 0, and no other subarrays can sum to 0 without overlapping the indices of this first subarray. This illustrates that in some cases, we may only be able to find a single valid subarray that satisfies the condition, and the result in such cases will be 1. This example also demonstrates the importance of correctly handling 0 and negative numbers when calculating subarray sums. Now let's consider some important constraints and edge cases. First, since the input guarantees that the array has at least one element, we don't need to handle empty arrays. However, the large size of the array, up to 100,000 elements, means that any solution with a time complexity worse than O(n) is likely to be too slow. Efficient strategies, such as using prefix sums and a hash set, are necessary to solve this problem optimally. Additionally, the solution must account for negative numbers in both nums and target, as this can influence the sums of subarrays. In edge cases where all elements are equal to target, the answer should simply be the length of nums, since each element forms its own valid subarray. Conversely, if no subarrays sum to target, the result should be 0. These considerations are critical to ensuring the solution is robust and efficient across all inputs. To solve this problem, we considered two primary approaches. The first is the brute force method, where we iterate over all possible subarrays of the input array, calculating their sums one by one. If a subarray's sum matches the target value, we count it and ensure that subsequent subarrays do not overlap with this one. However, this approach is computationally expensive. Since we examine every possible subarray, its time complexity is O(n squared, which becomes impractical for larger arrays. It also doesn't use any additional memory, but that's its only advantage. This method doesn't leverage any specific properties of the problem, making it inefficient for larger inputs. To improve performance, we need a smarter approach that avoids redundant calculations and uses the problem's structure to our advantage. That's where the optimized approach comes in. The optimized approach uses a prefix sum along with a hash set to track sums we've seen so far. Here's how it works step by step. First, we initialize the prefix sum to 0, create a hash set containing just the value 0, and start a counter to track the number of valid subarrays we find. As we iterate through the array, we update the prefix sum with the current element. If the difference between the prefix sum and the target value exists in the hash set, it means we've identified a valid subarray. In that case, we increment our counter and reset the hash set to ensure subsequent subarrays don't overlap. If the difference isn't in the hash set, we simply add the current prefix sum to the set and continue. This approach is highly efficient, operating in linear time since we process each element of the array exactly once. The hash set, while requiring additional space, allows us to avoid redundant calculations. By resetting it whenever we find a valid subarray, we ensure non-overlapping subarrays, which is crucial for solving this problem. The chosen strategy for this problem is the optimized approach using a hash set. The intuition behind this method lies in maximizing the number of non-overlapping subarrays by efficiently identifying valid subarrays without redundant checks. The prefix sum technique is a key part of this approach. It enables us to determine subarrays with a sum equal to the target in constant time by simply checking for the difference in the hash set. The real breakthrough here is the decision to reset the hash set after finding a valid subarray, which ensures that no overlaps occur. This makes the solution both elegant and effective. We chose this approach because it is highly efficient, with a linear time complexity that makes it suitable for large inputs. It's also straightforward, avoiding the complexity of nested loops. Most importantly, resetting the hash set guarantees correctness by enforcing the non-overlapping condition. While the additional space required for the hash set is a trade-off, it's a reasonable compromise given the significant performance improvement. Although this method may initially seem less intuitive than brute force, its advantages make it the ideal solution for this problem. When comparing the two approaches, the brute force method quickly becomes impractical for large inputs due to its quadratic time complexity. The optimized hash set approach, on the other hand, is both faster and more elegant. While brute force explicitly checks every possible subarray, the hash set method avoids redundant calculations by leveraging mathematical properties, specifically the prefix sum. This allows us to detect valid subarrays in constant time. In conclusion, the optimized approach is the superior choice for this problem. Its efficiency, simplicity, and ability to handle large inputs make it far more suitable than brute force. By combining the power of prefix sums and the hash set, it provides an elegant solution to the challenge of maximizing non-overlapping subarrays with a given sum. Here, we are tasked with finding all non-overlapping subarrays in a given array nums that sum up to a target value target. The goal is to maximize efficiency while ensuring that no two subarrays overlap. To begin, we can consider a brute force approach. This involves examining every possible subarray within nums, calculating their sum, and checking if it matches the target. If a valid subarray is found, we must ensure that its indices are excluded from consideration for any subsequent subarrays. To implement this, we start by iterating over all potential starting indices of subarrays using a loop, and for each starting index, we use another loop to define all possible ending indices. The sum of the subarray between these two indices is then computed and checked against the target. If it's a match, we record the subarray and mark its indices as visited to ensure subsequent subarrays do not overlap. While this method is straightforward, it is computationally expensive, making it impractical for larger datasets. To refine this brute force approach, we introduce a mechanism to skip indices that have already been marked as part of a valid subarray. Using a Boolean array called visited, we track which indices are part of previously identified subarrays. If we encounter a visited index, we skip it in future iterations. The process continues until all indices in the array have been processed. Looking at a pseudocode implementation, we see how this logic functions step by step. For each starting index, we check if it's already visited and skip it if necessary. We then calculate the cumulative sum of elements for potential subarrays, stopping if overlap is detected through the visited array. When a subarray matches the target, its indices are marked as visited, ensuring no overlap. While effective for ensuring correctness, this approach still involves nested loops, making it computationally intensive for large inputs. The pseudocode serves as a foundational understanding of how we approach the problem systematically. Analyzing the brute force method, we observe that its time complexity is O(n)² due to the nested loops iterating over all possible subarrays. This means that for each starting index, we must evaluate all potential ending indices, leading to quadratic growth in computation as the array size increases. To ensure non-overlapping subarrays, the visited array is crucial, as it prevents reuse of indices already included in a valid subarray. When considering edge cases, the algorithm handles scenarios where the input array is empty by producing no output, as there are no subarrays to process. Similarly, if no subarray sums to the target, the output remains empty. On the other hand, if multiple disjoint subarrays sum to the target, all of them must be included in the result. The visited array plays a dual role here, ensuring correctness by avoiding overlap and contributing to a space complexity of O(n). Together, these elements highlight the strengths and limitations of the brute force approach. Looking to optimize the brute force approach, we can explore techniques such as prefix sums. By pre-computing a prefix sum array, we can retrieve the sum of any subarray in constant time, avoiding redundant calculations. While this reduces some computational overhead, it does not eliminate the inherent O(n)² complexity of the brute force method, as we still iterate over all subarray combinations. Another potential optimization involves using the sliding window or two-pointer technique, which is particularly effective when the array contains only positive integers. This method dynamically adjusts the subarray boundaries, reducing the need for nested loops and improving efficiency in specific scenarios. When considering complexity analysis, the brute force approach maintains a time complexity of O(n)² due to the two nested loops, while the space complexity is O(n), primarily due to the visited array. These optimizations and their trade-offs are important to consider as we aim for a more scalable solution. To illustrate the brute force approach, let's walk through an example. Given nums equals 1, 2, 3, 4, 5, and target equals 5, we begin by examining subarrays starting at index 0. Subarrays like 1, 2, 1, 2, 3, and so on are evaluated, but their sums do not match the target. Moving to index 1, the subarray 2, 3 sums to 5 and is marked as valid. The indices 1 and 2 are then marked as visited. Continuing, subarrays starting at index 3 are evaluated, but none meet the target. Ultimately, the output is a single subarray, 2, 3. While this example highlights the correctness of the brute force method, it also underscores its inefficiency for larger arrays, as we repeatedly calculate sums and rely on nested loops. This reinforces the need for more efficient strategies in solving the problem for larger inputs. This implementation solves the problem of finding the maximum number of non-overlapping subarrays whose sum equals the target value, using an efficient approach with a prefix sum and hash set. First, we initialize the prefix _sum to 0, which will keep track of the cumulative sum of elements as we iterate through the array. We also initialize scene_sums as a set containing only 0, because the prefix sum for an empty subarray is 0. The count variable is initialized to 0 and will store the number of valid subarrays found. The loop iterates over each number in the input list nums. For each number, we update the prefix _sum by adding the current number to it. Then, we check if prefix _sum target exists in the scene_sum set. If it does, this means that we have found a subarray whose sum equals the target. When such a subarray is found, we increment the count by 1, reset the prefix _sum to 0, and reinitialize scene_sums to contain only 0. This is done to ensure that subsequent subarrays do not overlap with the current one. If prefix _sum target is not found in scene_sums, it means the target sum has not been achieved yet, so we simply add the current prefix _sum to the scene_sum set and continue. Finally, the function returns the count, which is the maximum number of non-overlapping subarrays whose sum equals the target. This approach is efficient, with a time complexity of O(n), as each element is processed exactly once, and the operations on the hash set are average O(1). This is the Java implementation of LeetCode problem number 1546, maximum number of non-overlapping subarrays with sum equals target. The code mirrors the logic of the provided Python solution. Key differences include the use of Java collections like hashset for storing scene prefix sums, type declarations for variables, and the structure of the Java class. The implementation efficiently tracks prefix sums and resets when a valid subarray is found, ensuring non-overlapping subarrays are counted. To solve this problem, we start with an example where the input array is 1, 1, 1, 1, and the target sum is 2. First, we initialize three key variables. Prefix underscore sum is set to 0 to keep track of the cumulative sum as we iterate through the array. Scene underscore sums is initialized as a set containing only 0 to store all prefix sums encountered so far, and count is set to 0 to count the number of non-overlapping subarrays that meet the target sum. Now, as we process the first element, which is 1 at index 0, we update prefix underscore sum to 1. We then check if the difference between prefix underscore sum and the target, which is -1, exists in scene underscore sums. It does not, so we add 1 to scene underscore sums. Moving on to the second element, which is also 1 at index 1, we update prefix underscore sum to 2. This time, the difference between prefix underscore sum and the target is 0, which exists in scene underscore sums. This means we have found a subarray that meets the target sum, so we increment count to 1, reset prefix underscore sum to 0, and reset scene underscore sums to contain only 0. This reset ensures that any subsequent subarrays are non-overlapping. Continuing with the array, we process the third element, 1 at index 2. We update prefix underscore sum to 1 and check if the difference between prefix underscore sum and the target, which is -1, exists in scene underscore sums. It does not, so we add 1 to scene underscore sums. Then, for the fourth and final element, 1 at index 3, we update prefix underscore sum to 2. The difference between prefix underscore sum and the target is 0, and it is present in scene underscore sums. This indicates another subarray that meets the target sum, so we increment count to 2, reset prefix underscore sum to 0, and reset scene underscore sums to contain only 0. At the end of the iteration, the total count of non-overlapping subarrays with a sum equal to the target is 2. Now, let's analyze a more complex example with the input array -1, 3, 4, -2, 2, 1, and a target sum of 5. As before, we initialize prefix underscore sum to 0, scene underscore sums to a set containing only 0, and count to 0. Starting with the first element, -1 at index 0, we update prefix underscore sum to -1 and check if the difference between prefix underscore sum and the target, which is -6, exists in scene underscore sums. It does not, so we add -1 to scene underscore sums. Next, for the second element, 3 at index 1, we update prefix underscore sum to 2. The difference between prefix underscore sum and the target is -3, which is not in scene underscore sums, so we add 2 to scene underscore sums. Moving on to the third element, 4 at index 2, we update prefix underscore sum to 6. The difference between prefix underscore sum and the target is 1, which is also not in scene underscore sums. Thus, we add 6 to scene underscore sums and proceed. Next, we process the fourth element, -2 at index 3. Here, prefix underscore sum is updated to 4, and the difference between prefix underscore sum and the target is -1. This time, -1 is found in scene underscore sums, which means we have identified a subarray with the target sum. We increment count to 1, reset prefix underscore sum to 0, and reset scene underscore sums to contain only 0. For the fifth element, 2 at index 4, we update prefix underscore sum to 2. The difference between prefix underscore sum and the target, which is -3, is not in scene underscore sums, so we add 2 to scene underscore sums. Finally, for the sixth element, 1 at index 5, we update prefix underscore sum to 3. The difference between prefix underscore sum and the target is -2, which is not in scene underscore sums. Therefore, we add 3 to scene underscore sums. At the end of this example, the total count of non-overlapping subarrays with a sum equal to the target is 1. Let's consider another example where the input array is 5, 5, 5, 5, and the target sum is 5. As usual, we initialize prefix underscore sum to 0, scene underscore sums to a set containing 0, and count to 0. For the first element, 5 at index 0, we update prefix underscore sum to 5 and find that the difference between prefix underscore sum and the target, which is 0, exists in scene underscore sums. This indicates a subarray with the target sum, so we increment count to 1, reset prefix underscore sum to 0, and reset scene underscore sums to contain only 0. Next, for the second element, 5 at index 1, we update prefix underscore sum to 5 again. The difference between prefix underscore sum and the target is 0, which is still in scene underscore sums. This marks another subarray matching the target, so we increment count to 2, reset prefix underscore sum, and reset scene underscore sums again.
Continuing with the array, we process the third element, 5 at index 2.
We update prefix_sum to 5 and find that the difference between prefix_sum and the target, which is 0, exists in scene_sums. This gives us another subarray with the target sum, so we increment count to 3, reset prefix_sum to 0, and reset scene_sums. Finally, for the fourth element, 5 at index 3, we update prefix_sum to 5 again. The difference between prefix_sum and the target is 0, and it is present in scene_sums. This means we have found yet another subarray, so we increment count to 4, reset prefix_sum, and reset scene_sums. At the end of this example, the total count of non-overlapping subarrays with a sum equal to the target is 4. The time complexity of this algorithm is O(n), where n is the length of the input array nums. This is because the algorithm processes the array using a single for loop, iterating through each element exactly once. This contributes a linear time complexity of O(n). Additionally, the set operations performed during each iteration, such as checking for membership and adding elements, are expected to take constant time, O(1), on average, due to the properties of hash tables. While hash collisions could theoretically result in these operations taking O(n), in the worst case, this is highly unlikely in practice and does not significantly impact the analysis. Therefore, the overall time complexity is determined by the single traversal of the array, making it O(n). The space complexity of the algorithm is O(n) in the worst case.
This is primarily due to the scene_sum set, which stores the prefix sums encountered during the iteration.
In the worst-case scenario, where all elements of the array contribute unique prefix sums, the set could grow to a maximum size of O(n). However, the algorithm includes a mechanism to reset the set to 0 whenever a subarray with the target sum is found.
This reset reduces the set size temporarily, thereby lowering practical memory usage.
Despite this optimization, the theoretical upper bound on space usage remains O(n). In addition to the set, the algorithm uses a few scalar variables such as prefix_sum, count, and number, which require constant space, O(1). Thus, the total space complexity is dominated by the scene_sum set, resulting in O(n). Now, let's compare the optimized solution to a brute force approach. The naive solution would involve iterating over all possible subarrays and calculating their sums to check if they equal the target. This approach has a time complexity of O(n², as it requires nested loops to evaluate all subarrays. Its space complexity is O(1), since it does not use any additional data structures. However, this inefficiency makes it impractical for larger input arrays. In contrast, the optimized solution leverages prefix sums and a hash set, reducing the time complexity to O(n), which is a significant improvement. While the space complexity increases from O(1) to O(n) due to the use of the hash set, this trade-off is worthwhile because of the dramatic reduction in runtime.
Analyzing the best, average, and worst cases provides further insight into the algorithm's performance.
In the best case, the array contains frequent subarrays summing to the target. This leads to frequent resets of the scene_sum set, which reduces its effective memory usage. However, the time complexity remains O(n), because the algorithm still processes every element in the array. In the average case, the algorithm maintains its linear behavior, with additions to the set and occasional resets.
Time complexity is still O(n).
The worst case occurs when no subarray sums to the target, meaning the scene_sum set grows to its maximum size of O(n). Even in this scenario, the time complexity stays O(n), but the space complexity reaches its upper bound of O(n). Mathematically, the total work per element in the for loop is constant, O(1), leading to O(n) work overall. Similarly, the maximum size of the scene_sum set, proportional to the number of elements in the array, confirms the space complexity is O(n).
When solving this problem, there are several common mistakes to watch out for. First, failing to handle edge cases properly is a frequent issue.
Scenarios like an empty array, an array with only one element, or when the target is 0 might not immediately come to mind, but ignoring them can lead to off-by-one errors or even runtime exceptions if your implementation doesn't explicitly account for them. Next, it's important to understand the concept of non-overlapping subarrays. Misinterpreting this can result in accidentally including indices that overlap, which violates the problem's constraints and produces incorrect results. Additionally, many solutions struggle with inefficiency. For example, brute force approaches with O(n squared) or O(n cubed) complexity often overlook optimizations like using prefix sums or hash maps. This inefficiency can quickly lead to time-limit-exceeded errors, especially when dealing with large input sizes, such as arrays with more than 10,000 elements. Another challenge is implementing the sliding window technique incorrectly. This often happens when the array contains negative numbers. Sliding window works well for non-negative numbers because the subarray sum behaves predictably, but with negative numbers, sums can fluctuate, making the technique unsuitable. It's also easy to misuse data structures, particularly when working with prefix sums. For example, using a hash set instead of a hash map can cause issues because hash sets don't store extra information like frequencies or indices. This limitation can lead to logical errors since tracking the frequency of prefix sums or their positions is often critical to solving the problem correctly. To excel in interviews involving this problem, there are several key insights to keep in mind. First, recognize that prefix sums combined with hash maps are an extremely powerful pattern for solving subarray problems efficiently, often achieving O(n) time complexity. For problems requiring contiguous subarrays, sliding window techniques are effective, but you must carefully handle constraints like ensuring subarrays are non-overlapping. Always test your code against edge cases to ensure robustness. Another important aspect is communication. Clearly articulate your reasoning when choosing an approach. For example, explain why using a hash map is advantageous compared to a brute force method. This demonstrates both your understanding of the problem and your ability to optimize solutions. Additionally, don't hesitate to ask clarifying questions about edge cases or constraints, such as whether the array can be empty or whether all numbers are guaranteed to be positive. Lastly, while optimization is crucial, it's a good idea to briefly outline the brute force approach first. This shows that you understand the problem comprehensively before diving into an optimized solution. This problem is closely related to several others on LeetCode that use similar techniques or concepts. Examples include Problem 560, subarray sum equals k, and Problem 523, continuous subarray sum, both of which involve finding subarrays with specific sum properties. Other related problems include 1248, count number of nice subarrays, and 930, binary subarrays with sum. These problems can serve as excellent practice to deepen your understanding of prefix sums and hash maps. Additionally, there are various approaches to solving these problems beyond the optimal ones. For instance, a brute force solution, while simple to implement, is usually inefficient with a time complexity of O(n squared) or O(n cubed), making it suitable only for small input sizes. On the other hand, using prefix sums with a hash map is optimal for time complexity, operating in O(n). However, this approach does require additional memory, which might become a concern for very large arrays if the prefix sums are unique. Finally, if all numbers in the array are non-negative, sliding window techniques can be highly efficient in space-saving, running in O(n), but they won't work if there are negative numbers in the array. For more complex variations of subarray problems, dynamic programming may be a better approach. This is particularly true when the problem involves cumulative or state-dependent constraints that can't be handled with simpler techniques like prefix sums or sliding windows. The trade-off with dynamic programming is that it tends to be harder to implement and debug compared to other methods. However, it can be a powerful tool for tackling challenging constraints that require tracking multiple states or conditions simultaneously. Thank you for watching. Today, we explored an interesting problem and learned about different approaches to solve it. Remember to practice and apply these techniques to similar problems. Stay tuned for more coding solutions, and happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!